So let us take up the fundamental theorem of calculus part 1 as described on the page 50 of your textbook. Okay, so what it says is this, that is, if you have a continuous function of x over an interval a, b, and here they mean a closed interval. This is the, in this case we are different. This is t-axis and this is ft-axis. All right, and you have a continuous function f of t. Then you can form a new function fx by doing what? By simply taking the area between a and x, where x is also varying along this t-axis. And then, so if you change x, since the function is continuous, the area is available, so you'll have different values of capital F, and that's how you have formed a function. So that function will be a differentiable function, and the derivative of that function at x would be how much? Simply this original function, this function f evaluated at x. All right. So let us consider a continuous function f that's defined on the, let's say we are taking over the interval -2 to 10, and we shall take up the function capital Fx as, and here is our t-axis, and here is our ft-axis, okay? And we are taking the function capital Fx as the integral from -2 to x ft dt. Okay, so if I look at, for example, value of the function big F at 0, what that will be -2 to 0 ft dt, and we can have Desmos calculated by simply doing this, that ask it to give us the integral from -2 to 0, that of f, function f, and you can see right here I have defined the function. So this is like 2.5075. So that's about if you look at it, that's about this area, okay, from -2 to 0. Now say we want to obtain the value of the function big F at 4. I can simply do this, just go to the integral and change this upper limit to 4, and that value is about 0.96601, that is. So the area from -2 to 4, this whole area, like the area here and here, it's approximately 9.6601. So that's how we obtain, various values of this function capital X defined in this way. And let me just go ahead and superimpose it right here for you, okay, by erasing this graph. So let me first erase all the drawings, and then, so for example, you had seen that F4 was approximately 9.6. Okay, so here it is, it's approximately 9.6. Or if you want, what you can do is this, that go ahead and say, for example, you want, F0, it is the same 2.5074 as you had obtained before. And if you want, you can keep on changing it here. F1 is like about 3.206, and F2 is about 5.01. As you can see, right here is 5, so that's about 5.01, and the graph is too thick anyways. Or you can do this, If you want, you can do it a little more dynamically, like take b equals, for instance, you can take b equals, say, let's take 3, and we will let our b go from -2 to 10, okay, and sorry, not there. Okay, we took b as 3, -2 to, we wanted it to be 10, and step we can take anything, let's take 0.1, and then we can see this, like right here, sorry, we can make this to say be here, okay, right here. So we got the value of f, which is given by this, to say at 3 as 7.15. This appears to be right. And when you say, just take this slider here, and so then f at 4 is 9 points. Actually, I said 9.6. It is 9.66, I'm sorry. And then it just keeps on changing the values for you. And then if we want to apply the theorem, now say we want here the slope of the tangent line to the graph of this big F at 2, then all that we have to do is look at the value right here of the function little f at 2, which is about 1, and you can see that this is about this whole thing is about 1. Sorry, this is about 2. I said it wrong because these scales here are going 2, 4, 6, 8, 10. And here on the horizontal side, this is about 1. So this is 2 and the slope is 2. So again, to obtain the slope of the tangent line to the graph of big F, all we have to do is evaluate the small f at x. All right. So let me erase all this drawings that I made and we go a little further. Okay, so for example, say instead of this function, say I change the function to, let me just make a different function here. Okay, I'm going to make a function, make a function gx where the upper limit, instead of being x, as sine of x, and so you shall see. Why did the graph not show up yet? Just a second, please. Yes, here it is. Took a little while. Let me just change the color of this. That is just to distinguish. Let's make it orange. So yeah, so here is the graph of gx. Now say we would like to get the derivative of g at 2, okay? So the best thing is that notice this, we have gx equals this. I don't know why I'm writing it again, but anyways, so instead of x, I have sine x here. So as you did before when using the chain rule, let's take u as sine x. So g is -2 to u f t dt. So dg dx, which is actually g prime of x, is going to be dg du, just using the chain rule, and then du dx. And who dg du will be? Right here, the fundamental theorem of calculus will apply, and that will be f of how much? U. And du dx will be how much? Du dx will be u is sine x, so du dx will be cosine of x. Okay? So when we are writing g prime of 2, what we shall have is f of, you see, you have u, so who is u? Sine of x, but what we are doing is we are taking sine of 2 instead, and then we have cosine of x, which will be cosine of 2. So this is what the value of g prime 2 will be, and we can now go ahead and substitute t equals sine 2 here, okay, and obtain the value. Or since we are already using this calculator, so we can always just write sine of 2 here, okay, and that's the value of f, okay, and then we can, if you want, here, let's just do this here. Right here, we should multiply it by the cosine of 2, okay, because if you recall, that's what we are using here, and the slope at x equal to, for the orange line, is like negative, about approximately negative 0.5, and you know the way the scales are here, okay, this whole thing is 1, so if you draw the tangent line, that's what that will approximately be. And in this case, I think we should also be able to get g prime at 2, like just have the calculator give that to us, g prime at 2, and so we had g of x equals that, yes, here it calculated, it took a little while, okay, and both of them are the same. All right.